Okay, let's unpack this fantastic stack of sources.
Let's do it.
We are diving deep into, the black box of large language models. But today we're skipping the surface entirely.
Mm.
Today's mission is to really analyze the internal mechanisms of the transformer architecture itself.
And critically, how to optimize them.
Exactly, with this new technique called bottom-up policy optimization, or BBPO.
Yeah, and that's the key shift, right? We've usually treated an LLM as just one single thing, a monolithic policy,
One big brain.
one big brain. But these sources, they let us look inside and see how the decision-making, the actual policy, sort of evolves layer by layer.
And this is where we crack the black box open. The
Mhm.
big discovery is that the overall LLM policy secretly contains these internal layer policies.
And internal modular policies, too.
Right, for things like self-attention and the FFNs. So let me get this straight. These are calculated by combining the internal hidden states, the model's running notes, with the unembedding matrix.
You got it.
Which is basically the model's final translator that maps its internal numbers back into, actual words.
Exactly. By using that final translator at every single step, we can see what prediction each layer would make if it had to decide right then.
Ah, okay.
And analyzing that revealed this universal internal reasoning structure across all the models they looked at.
Measured by internal policy entropy.
Right. And you can think of high entropy as the model just throwing out 20 different possible answers. It's exploring.
Casting a wide net.
Precisely. Early layers have this high entropy, but the top layers consistently converge to near zero. They get very confident for the final prediction.
That makes sense. But the way they converge is the architectural aha moment. This is what you, the listener, really need to hear.
Mm-hmm.
The Llama models, for instance, they show this really sudden convergence.
It's like a cliff.
Yeah, their decision space just collapses, but only in the last few layers, maybe the final three. It's like a student cramming for an exam the night before.
That's a great analogy. And in sharp contrast, you have the Qwen series, especially Qwen 3.
Which is different.
Totally different. It shows what we might call a more human-like progressive pattern. Its FFN layers follow this really clear three-stage exploration, integration, convergence progression.
So it's more methodical.
Much more. This staged approach, it's hypothesized to be qualitatively similar to how a person actually solves a complex problem.
So if architecture dictates behavior, if Llama is a last-minute crammer and Qwen is a structured planner, that raises a huge question for training, doesn't it?
It does.
Because traditional reinforcement learning, like PPO, it only grades the final answer. It misses all that development happening underneath.
Absolutely. And that's the motivation for this new paradigm, bottom-up policy optimization, BBPO.
So if reasoning emerges from the bottom up,
Then your reinforcement learning should align with that structure.
okay, so BPO is the solution here. It's an RL paradigm that sequentially optimizes the internal layer policies first, like, say, layer 6, and then it optimizes the overall model policy.
Exactly.
Yeah.
The mechanism is really elegant. BPO isn't just grading the final exam. It's tutoring the student throughout the entire semester.
I like that.
By optimizing those lower layers first, you're forcing them to capture high-level reasoning information preemptively. This feature refinement just establishes a much more robust foundation for everything that happens later.
And the results seem to back this up.
They do.
BPO consistently gets superior average performance compared to, say, GRPO or PPO on these really tough reasoning benchmarks like math and AIM.
Qwen 3.4b saw some really significant gains on AIME 24 and 25.
But this whole process is a tightrope walk, isn't it? It's not that simple.
It is a very delicate balance. The sources are clear on this. There's a critical caveat. The optimization have to be moderate.
And if you push it too far?
If you push it too far, you get a complete performance collapse. The mismatch between the different policies just becomes too severe.
So it's all about careful calibration.
It is. It confirms that layer-aware optimization is highly effective, but you have to be smart about it.
Which brings us to a fascinating final thought, building on that Llama and Qwen contrast.
Okay.
If a model's foundational architecture really dictates its intrinsic reasoning pattern like that progressive EIC structure we see in Qwen 3, then how much does the base model's initial design predetermine the ultimate effectiveness of any post-training you try to do?
Wow, yeah.
Is the race kind of won before the optimization even begins, something for you to mull over until our next deep dive?